Hello students, welcome to this presentation. I would be trying to give 3 presentations basically on thin and thick cylinders. These presentations are a part of EduSat program on strength of materials initiated by Visvesvaraya Technological University, Belgaum. Now, coming to some of the contents of this particular program, which comes under module 2R, the introduction, then thin and thick cylinders, basically thin cylinders subjected to internal pressures, what we understand by hoop stress, longitudinal stress and change in volume on thin cylinders. We also talk about thick cylinders subjected to both internal and external pressures. And finally, the most important equations in thick cylinders, that is Lamè's equations, which tell us about the way in which the radial stress and hoop stresses are distributed over the wall of a thick cylinder. Now, basically at the end of this 3 series of presentations, the student will be able to learn the differences between the thin and thick cylinders, the stresses developed in thin cylinders, the formulations for circumferential and longitudinal stresses in thin cylinders, the dimensional and volume changes that a thin cylinder will undergo, and some basic design principles covering thin cylinders. Now, further on, the student will also have the ability to understand the knowledge on thick cylinder theory, the assumptions that we make in thick cylinder theory, the types of stresses that are present in thick cylinders, and a very important derivation which we normally call as Lamè's equations for both circumferential and radial stress distribution, and finally some basic design principles in thick cylinder. Now, these are some images which try to tell you some of the types of or cylinders that are being used. So, you can clearly see the cylinders are quite huge. So, these are some typical cylinders being applied. So, I just want you to just have a comparison of the size of the cylinder with respect to the persons working over there. For example, the diameter is almost equal to the size of the men who are working there. So, another picture which shows that the person is right within the cylinder. These are in the fabrication stages. Again, you can clearly see the openings in the cylinders. So, there are joints which we are going to just talk about later. Okay, and again you can clearly see a huge cylinder being lifted, and you can just try to see in the background, okay, some buildings. So, you can imagine the size of cylinders, okay, that can be in reality. Now, before we go on, I would like to just talk about some general introduction with respect to strength of materials. Now, I understand before this series of lectures, you have heard 2 presentations by my colleagues on simple stresses and strains and compound stresses. So, if you just try to understand, just have a quick review, they are very relevant to this topic, that is thin and thick cylinders. So, let us quickly recapitulate some important things about the concepts that you have already learned in simple stresses and strains. Now, in simple stresses and strains, as the name itself indicates, we are talking about a body which is subjected to only one type of stress, okay, and that too only one number it could be a body subjected to a simple uniaxial direct force, axial force, it could be tension, it could be compression, or a body subjected to a shearing force. Now, as you understand, in simple stresses and strain, when I say stress, stress is nothing but the resistance offered by the body when it is subjected to external force. As you understand, the stresses can be of two types, the normal stresses and shear stress. These are the only two types of stresses that can develop in a body, or we can idealize the stresses into two categories. One is normal stress and the other is shear stress. As the name itself indicates, normal stress is a stress which acts perpendicular to the surface, the reference surface that we are talking about. And when you say shear stress, it is the stress which acts parallel to the surface. So, please understand, all types of stresses can be either categorized as normal stress or shear stress. So, we cannot have any other stress. I think this you have to make yourself very clear. Only two types of stresses, normal stress or shear stress. In simple stresses and strain, you just talked about only one normal stress or only one shear stress, and you try to analyze the problem. Now, stress is a measure of internal resistance. Now, coming to the next parallel thing that we talk about is the strain. Now, strain is a measure of the deformation in a body. The very first thing that we need to understand in strength of materials is all bodies deform when you subject them to some kind of loads, and these deformations are quantified in terms of strains. Now, there are two types of strains that we try to associate with these two types of stresses. Now, coming to normal stress, we try to talk about what are called as linear strains. So, linear strains can be quantified in terms of the three directions like x, y and z directions. And when you just try to talk about shear strain, it is quantified with respect to, or it is compared with respect to shear stress. Now, when you just talk about shear strain, it is nothing but the angular deformations that the body undergoes. If you just try to take a body, subject it to some kind of shear force, you can easily expect the body distorts itself. That means, if you just try to take a cube and then try to apply a force on the top surface, keeping the bottom surface fixed, upon the application of the top force, you expect the cube to deform. So, you can easily understand there is a change in geometry, that is, there is angular deformation. Whenever angular deformation takes place, we try to quantify in terms of shear strain. So, when you are just trying to make some calculations, and if the value of shear strain you get is high, you need to understand that the body has geometrically changed, that is, the shape has really changed. So, these are some important concepts that you need to understand with respect to the strains. Now, the next important topic that you already been taught is the compound stresses. Now, in compound stresses, the discussion was about an element which is subjected to two or more stresses. Like when I say two or more stresses, it could be a combination of two direct stress, or one direct and one shear stress, or two direct and one shear stress. It could be anything. So, we are just trying to understand how an element will try to behave when it is subjected to more than one type of stress, that is compound stresses. So, it is an extension of what we learned under simple stresses and strains. Now, this two topics, that is simple stresses and strains and compound stresses, okay, forms a prerequisite to this particular course or this particular topic of thin and thick cylinders. Now, coming to the concepts of thin and thick cylinders, as you can understand, basically they are cylinders, okay, which are subjected to internal pressures or both internal and external pressures. And we are basically trying to understand, okay, how to analyze a cylinder subjected to these kind of pressures. Now, coming to some different applications of these cylinders, basically they are used as pressure vessels. It could be like pipes, steam boilers, storage tanks, etc. So, some of the pictures that I showed to you were about these kind of applications. As I did mention, these cylinders, okay, carry gas or fluid under pressure, and we can just try to talk about these pressures being internal and external. Now, the very first thing that we need to understand here is, when do we call a cylinder as a thin cylinder and when do we call a cylinder as a thick cylinder? So, normally some cylinder will be there, and we always try to have two dimensions or two parameters connected to a cylinder. One is the diameter. When I say diameter, basically we are trying to talk about the internal diameter, and then we have the thickness of the wall. So, if I just try to give you a problem saying that, look, I have a cylinder whose diameter is 1000 millimeter, okay, or it could be 2000 millimeter, or it could be 500 mm. Okay. Is it a thin cylinder or is it a thick cylinder? Basically, it is not possible for us to classify a cylinder into a thin cylinder or a thick cylinder by just giving only the diameter. Okay. We try to basically compare, we need to compare the diameter with respect to the thickness and then try to understand the thicknesses, okay, in what proportion to the diameter, and then come to the conclusion whether the cylinder is thin or thick. For example, if we just try to look at this particular video, right. So, the first cylinder, okay, we have here as a thin cylinder, and the next one is a thick cylinder. So, basically, though the internal diameters, okay, could be the same, okay, the cylinder can be thin or thick. How do we decide whether the cylinder is thin or thick? Okay, you need to understand, if the thickness of the cylinder, okay, is less than about 10% than the diameter, then we can call it to be a thin cylinder. And if the thickness of the cylinder is more than 10% of the diameter, then we call it to be a thick cylinder. Please understand, this 10% is just an approximate thing. Okay. So, most of us may not agree with respect to 10%. Some say it is 7%, some even can say up to 20%. But basically, for us, the comparison is, okay, the thickness to the diameter. So, if thickness is relatively small when compared to the diameter, so you can always say that the cylinder is thin, otherwise it is thick. When say relatively, here I am trying to take it as 10%. Now, understand that in case of thin cylinders, right, because the wall thickness is small, right. So, the pressures it is going to carry, internal pressures it is going to carry, obviously is less. You cannot have the cylinder subjected to higher internal pressures. Whereas, if you just try to take a thick cylinder, okay, it is more capable of trying to resist more internal pressures. So, you need to understand, it all depends on the usage, the practical problem. So, if you have an issue where the pressures are high, so obviously we should have a larger thickness, and then we are trying to design it as a thick cylinder rather than a thin cylinder. So, we just try to go back to this presentation, this video again. Okay. So, please understand. So, the diameter we are trying to reduce it. Okay. Here the diameter we are that is thickness is going to increase. So, in the first case thickness is small, second case is thickness is large, right. Okay. So, let us try to go to the next one. Okay. Now, basically how many types of stresses do we have in cylinders? As I was trying to tell you, we are trying to have a problem here which is of compound stress in nature. So, basically here the walls of the cylinder are subjected to what is called as triaxial state of stress. So, that means there are three stresses, triaxial, there are three stresses, tri-stresses, and what are the types of stresses? They are axial stresses. So, what you need to understand is the stresses are acting along the x direction, the y direction and the z direction in an element. Okay, that is, there are three stresses. You need to understand all are axial stresses. So, there is no shear stress we are talking about. Okay, all are axial stresses. Okay, this first thing that you need to understand in compound stresses. Okay, we are trying to talk about a triaxial state of stress. Okay, the stresses are acting along three axes of an element. You can visualize it as the x axis, the y axis and the z axis. And these stresses, okay, are called as the circumferential stress, which is denoted by sigma c, then the longitudinal stress, which is denoted by sigma L, and the third one is the radial stress denoted by sigma R, that is triaxial. These are the three stresses that we are referring to in the wall of a cylinder. Now, just try to look at this animation. So, this is again a cylinder. As you can clearly see, the length of the cylinder is L, it has an internal diameter of D and the thickness is T. Now, this video shows about the stresses in the wall of the cylinder. So, what we are trying to do is we are trying to take, okay, a small piece, an element from the wall, and we are just trying to take it up, and you are trying to see the three stresses over there. Okay, the first one, as we understood, is the circumferential stress sigma c, the next one is the longitudinal stress sigma L, and third one is the radial stress. Okay, I hope trying to understand. Okay, if I just try to repeat this again, okay, so you can just try to see this. So, we are just trying to take a small piece from the wall, just trying to blow it up, and you see the three stresses. These are axial. Okay, all are normal stresses. So, one acting along x direction, one acting along y direction, one acting along the z directions. Now, coming to more about the three stresses themselves. Okay, what are the three stresses? The first one is the circumferential stress. This is one of the important stresses that we refer in a cylinder. Basically, it is a normal stress. I hope you know what is a normal stress. It is a stress which acts normal to the surface, perpendicular to the surface. Okay. Next, it acts along the circumference of the cylinder. Okay, it acts along the circumferential direction. So, if you just try to take a small element, okay, it acts along the circumferential direction. So, you need to understand how exactly the circumferential stress acts. It is also referred to as the hoop stress or the girth stress, some other names that we just try to give this particular stress as. And finally, it is denoted by the notation sigma suffix c. So, again, if you just try to look at this animation, you will just try to see that, okay, the direction of sigma c, okay, which is being animated over there. So, again, we are trying to take an element from the wall of that particular cylinder. Okay. So, only sigma c, we are just trying to show you, it is trying to move. Okay, and this sigma c is acting along the circumferential direction. So, I hope you have understood the first stress that we are trying to talk about, that is the circumferential stress. So, let us try to go to the next stress, that is the longitudinal stress. It is also a normal stress and it acts along the length of the cylinder. The first one was along the circumferential direction. Okay, now it acts along the length, okay, right, along the larger direction, right, the length of the cylinder. Okay, and it is designated by sigma suffix L. L stands for longitudinal stress. Now, again coming to look at this animation. So, again the same element we are trying to talk about here, okay, and you can clearly see that the stress along the longitudinal direction is animated, and that is the stress we are trying to refer here. There is stress acting in along the length, okay. So that is sigma L. So I hope you are trying to understand the second stress that we are trying to refer here. Now coming to the next one, that is the radial stress, okay. Now just try to look at this. It is also a normal stress like the circumferential stress or the longitudinal stress. It acts in the radial direction, that is the third direction. The first was along the circumference, then it was along the length, and fine, now this is the third direction, okay. It acts along the radial direction, and it is designated by sigma r, right. Now again, if you just try to look at this animated view, so again the same element, now you are trying to see that the stress along sigma r is being animated. So in total, I hope you have understood that, okay, if you just try to take any element, okay, which is subjected to some internal pressure, okay. So and if you just try to look at this element, it is basically subjected to three types of stresses, okay. One is the circumferential stress, the second one is the longitudinal stress, and third one is the radial stress. So this forms, okay, the most basic information with respect to stresses in the walls of a cylinder. That is the types of stresses that we are talking about in the wall of a cylinder, okay. Now the next one is the bursting force. What exactly is a bursting force? It is quite common sense. So we just try to take a that is a pipe, and if you just try to subject it to some internal pressure, right. So as the pressure goes on increasing inside, so the tendency is it forms a resultant force, okay, within the cylinder, okay, and then it tries to burst the cylinder, okay, into two portions, something like that, okay. So what you need to understand here is it is nothing but the resultant force which develops due to internal pressure, and this particular force tends to burst the cylinders basically into two portions, okay, and that is called the bursting force. So you need to understand that as the pressure increases, the bursting force also increases, right. And when does the cylinder burst? You need to understand it bursts at a critical pressure, okay, at which time, okay, the stresses in the walls of the cylinders, okay, exceed the permissible limits of the material. So you can expect at that instant, okay, that the cylinder may burst, okay, into two portions. Now let us try to understand how exactly this bursting force acts. So again, I am just trying to show you, okay, an animated view, okay, of a cylinder. So right now I have a cylinder which is subject to some internal pressure, right, something like that. Now understand that the pressure keeps on increasing. So we can expect once the pressure keeps on increasing, the stresses, the three stresses that we are trying to talk about, the circumferential stress, the normal stress, that is the longitudinal stress, and the radial stress keep on increasing. Now once, okay, this reaches some critical value, you can expect that the cylinder bursts into two portions, and what you are trying to see is that force, okay, bursting force, okay. So that is F, whatever you are trying to see there is the bursting force which tries to tear the cylinder in two portions. You can clearly see there is a split, okay, I am just trying to show you, okay, which separates the cylinder into two halves, okay, and that vertical force which I am trying to animate is the bursting force. Now the next important thing we are trying to talk about is how do we calculate the value of this bursting force. So this bursting force is calculated as the product of the pressure P, that is the internal pressure P, multiplied by the projected the curved surface projected on a horizontal surface, like for example, that particular, you are trying to see that in the animated frame, that is D is the internal diameter, okay, of that curved surface, Okay. So, that is the projection, the projection of the curved surface is nothing but d itself, okay, and let us assume that it has some length L. So, you can understand that the projection is d into L, right, and the pressure multiplied by the projected area of that curved surface, internal curved surface, gives you the bursting force. So, it is a very simple calculation. Okay, we can understand how we are able to get this bursting force. Understand this bursting force, okay, is required, okay, for us to calculate, okay, the circumferential stress in the thin cylinders. So, please understand this calculation. So, bursting force is calculated as the product of internal pressure multiplied by, okay, the projection of the curved surface, okay, on a horizontal surface or a horizontal plane. So, that would be d into L, right. Okay. Now, with this, let us start the first theory that we are supposed to discuss, that is the thin cylinder theory. We are talking about what is called as the thin cylinder theory. Now, when you just talk about any theory, okay, we are just trying to make some assumptions. Now, even in this theory, okay, we are just trying to make some assumptions. Now, assumptions really help us to simplify the problem enormously. Now, unless we make some assumptions, it is very difficult, okay, to do analysis. So, there are two important assumptions, okay, that we are trying to make in this thin cylinder theory. So, I hope you are aware that when I say thin cylinder theory, okay, the thickness of the wall of the cylinder is relatively small when compared to the diameter, and this cylinder is capable of carrying small internal pressures, okay, not large, because the thickness is small. So, for this particular cylinder, let us try to understand, okay, what are the assumptions, okay, that we are trying to make here. Okay. The first one we are trying to understand here is the magnitude of the radial stress is small and is neglected. Now, once you read this statement, you need to understand that right at the beginning we did mention that in any wall of a cylinder there are three types of stresses: the circumferential stress, the radial stress, and the longitudinal stress. Okay, three triaxial states stress system, triaxial stress, state of stress, three normal stresses. So, of these three normal stresses, okay, we are ignoring one, that is the radial stress. So, that means what? We are left with two other stresses, that is the circumferential stress and radial stresses. So, we are ignoring one stress, which is radial stress. Now, we need to understand why are we trying to ignore this radial stress. Okay, point number one. Okay, if we just try to make a comparison of this stress, that is the radial stress, with the other two stresses, which are nothing but the circumferential stress and longitudinal stress. So, basically this value is small, that is very small, okay, and hence is neglected. So, it does not mean that radial stresses are not present, okay, in the wall of a thin cylinder. It is present, okay, and it basically varies from, okay, whatever pressure, the stress, I am talking about stress, the radial stress varies from whatever internal pressure that the cylinder is being subjected to at the internal surface to 0 at the outer periphery. So, over the thickness of the wall at the interior surface, the stress is equal to the internal pressure, and on the outer surface, okay, the stress is 0. So, there is a variation, okay, but please understand the internal pressure, okay, is very small, okay, can be about 1 megapascals, 1.5 megapascals. So, it varies from about 1.5 megapascals to 0 over a very small thickness, okay, and understand this makes us to ignore the radial stress. So, it does not mean that radial stress is not present, it is present, but it is not significant when compared to the circumferential stress or the longitudinal stress, and that makes us to ignore this stress. Now, coming to the next important assumption that we are trying to talk about is the distribution of the circumferential stress. So, for example, if I just try to go to the blackboard here, so if I just try to draw the cylinder, something like this cylinder, right. It has some diameter d and it has some thickness t over here. So, that is the thickness. So, as you understand, the circumferential stress acts in the circumferential direction. So, if I just try to show the variation of the circumferential stress. So, normally it is more here, that is in the interior surface, and less at the outer surface, and there is a variation of stress. So, this is sigma c, that is it acts along the circumferential direction. I am just trying to cut the wall of the surface. So, as you understand, the circumferential stress is a normal stress. So, this stress is perpendicular to the cut surface, point number 1, and point number 2, it varies, strictly speaking it is going to vary. So, it is maximum at the interior surface, and it is minimum or it reduces at the outer surface. Generally the variation is non-linear. Now, the most important thing that we need to understand here is, if you just try to take the average value of this stress or this thickness and compare that average stress with the maximum circumferential stress which occurs at the interior surface, that difference is very small. So, what I am trying to tell you is the variation of stress from the interior to the exterior is very small, or the mean stress when compared to the maximum stress is very small. So, that being the case, so what we are trying to do is we assume that the circumferential stress is uniformly distributed, unlike here which is non-uniform, that is it is varying. Strictly speaking, this is how it has to be, but because the variation is small, in thin cylinder theory we assume that the variation is uniform. So, this is assumption number 2. So, assumption number 1, the stress in this direction, that is if we just try to take an element, the stress in the radial direction, any element, right, is small, we ignore. So, that leaves us with the circumferential stress and the next stress which is acting perpendicular to the this surface, that is along the length of the cylinder. So, only 2 stresses are present, and the next important assumptions we are talking about is the variation of sigma c right is considered to be uniform, because the average stress if you just try to compare the average stress with the maximum stress it is very small. So, that is about the assumptions. So, again one more animated view of this, that is sigma r, we are just trying to say it is 0. So, this is the most important thing that we are trying to talk about, that is with respect to the assumptions. Now, having finished the assumptions, the next important thing that we are trying to talk about is how we are able to get the expressions to calculate the stresses in the walls of a cylinder, thin cylinder. So, as the assumptions pointed out, we are trying to talk about only 2 types of stresses here. What are they? So, we have the circumferential stress, and then we have the longitudinal stress. So, my next discussion would be how exactly we are trying to get an expression to calculate the circumferential stress in the wall of a cylinder, and how exactly we are trying to get an expression to calculate the longitudinal stress in the wall of a cylinder. Now, if you just try to look at that animated view, so we are trying to consider a cylinder which is subjected to an internal pressure, as you can clearly see there. So, the cylinder has dimensions of d, that is internal diameter. So, do not get confused. So, generally when we say diameter, it is always by default the internal diameter is what we are referring, always internal diameter. So, we have an internal diameter d, small d over there. It has some thickness T and it is subjected to an internal pressure P, small p. Okay. Now, what are we trying to do here? We are trying to get an expression for the circumferential stress. So, the very first thing that we need to understand here is how does the circumferential stress act? As we have understood, the circumferential stress acts along the circumference, okay, in the direction, okay, of the circumference is what you need to understand. So, once you realize that, you need to understand how exactly we try to consider the free body diagram. So, when you try to talk about the free body diagram, I hope you know we need to cut the cylinder into two portions, okay, such that the circumferential stresses are released, okay, and you can apply your equilibrium equations and then compute the circumferential stress. So, that is the most important thing that you need to understand. So, just try to take a look at that picture that is there on the screen. Okay. So, we are just trying to take a longitudinal section. Okay. That means you have a pipe and you just try to take a slice along the longitudinal direction. AA is what you need to understand. That means, if I again go back to the board here, okay, that means I am trying to take a cylinder here, trying to take a cylinder, okay, that is a cylinder we are trying to talk about, trying to take this one, right. Okay, I need to cut the cylinder in this direction, okay. Once I cut this, you can understand that, okay, if I just try to take, okay, if I just try to take the upper portion, okay, you need to understand that the stress here gets exposed, right, gets released, okay, and what is the stress? That is sigma c. So, this is important, how we take the section, okay. So, that is a longitudinal section. So, okay, if you take the cylinder, cut it, okay, and then write the free body diagram of this, very simple concept, okay, and that should lead us to an expression for the circumferential stress. Okay. So, when we do numerical examples, okay, we want to calculate, okay, what is circumferential stress present in the wall of a thin cylinder. Okay. So, let us try to find out, okay, how do we do this. Okay. So, let us try to now, okay, cut the cylinder, okay, and then understand how exactly we get this circumferential stress. It is a very interesting thing that we are trying to have here. Okay. So, just try to look at this, okay, the same one, okay, we are just trying to show you a small animated view of this, okay, it looks very interesting. Okay. I am just trying to take, okay, I am going to just try to take up the top portion, okay, and then, okay, I am just trying to show you, turn that and then trying to show you. So, you are going to see two important things over there. Okay. The first one is the bursting force, capital F, the bursting force. Okay. The cylinder is being, okay, it's trying to burst into two portions, okay, and I hope you remember, okay, we have discussed as to how we calculate this bursting force, okay, before we started a thin cylinder theory, right. So, that is F is the bursting force, and there are two other forces you are trying to see there, okay, which is on the wall of the cylinder, okay, there are forces, right, the resultant, right, of the stress, two forces. Please understand, okay, there are two walls, okay, have been cut, right, two walls have been cut, because when it bursts, okay, the wall here and the wall here gets cut, okay, and hence we are writing two forces, okay, at the cut surface, P and P, they are equal forces, right, because of symmetry. So, the first one is the bursting force, okay, the second one is the resisting force. This resisting force, okay, is developed at the wall of the cylinder, right. I hope you have clearly understood this simple concept that we are trying to have here, right. So, bursting force, and the next one is the resisting force. So, I will just try to take you back through this presentation. Is it all right? So, okay, right from the beginning, right. So, the cylinder is turned, okay, and these are the bursting and resisting forces, okay, that are present, okay, in the wall of a cylinder, right. Please understand, a very simple equilibrium equation, okay, should give me, okay, the value of the circumferential stress. I guess all of you are now trying to understand, okay, what is this equilibrium equation we are trying to apply, in which direction. So, what you are seeing right now on the screen is the free body diagram, that is which we call as the FBD. So, let us try to go to the next slide. So, anyway, what you are trying to see there, a picture, okay, is the same one as I did explain. So, there is a bursting force F, okay, which is acting down over there, and there are two resisting forces P, okay, acting upwards, okay, on the wall of the cylinder. Okay. So, bursting force downwards in that cross section, it has to be downwards. I am just trying to take the lower half, okay, of the cylinder, okay, which is trying to separate, okay, and the next one, okay, is the resisting force. Now, this is force, is what you need to understand, is what I have written is the resisting force. Now, can you imagine, okay, how we have got this resisting force? Please understand, this resisting force is nothing but, okay, the resultant of the circumferential stress, right. So, I hope you know, in simple stresses, okay, you have heard we calculate the stress as, or we calculate the force as stress into area, or stress is nothing but the ratio of the force by area, right. That is force divided by area will give you stress, or if you rearrange, okay, force equal to stress into area. So, when you are calculating this resisting force, okay, that is P, okay, you need to understand that we are trying to take it as the product of, okay, the circumferential stress, okay, and the area over which, okay, this circumferential stress is going to act. Now, the circumferential stress is acting over the entire length of the cylinder. So, we are applying a simple equilibrium equation here, that is sum of the vertical forces, okay, in that FBD equal to 0. Okay, as you can clearly understand, if I just try to apply this equilibrium equation. So, I have, okay, a P acting here, that is P and P acting here, okay, and one more F acting here. So, that is the bursting force, so that is the resisting force P. Okay. A simple equilibrium equation like sigma, sum of all the vertical forces equal to 0. Okay. The moment you see sigma, I hope you know that that is an equilibrium equation. We are trying to take all force acting in the vertical direction or in the y direction equal to 0. Because it is an equilibrium equation, we need to have a sign convention, and the sign convention that I am trying to take here is upward forces positive, correct. And if you just try to look at here, there are two forces which are acting in the upward direction and one force acting in the downward direction. These two forces are of having the same magnitude, and hence I can write this as 2p minus f equal to 0, right. So, that is a simple expression. Okay. What we are trying to see is a very simple expression. There is 2p minus f equal to 0. What you have written is in terms of force, okay, 2p minus f equal to 0. The next one is, okay, what is this p? P is because of this circumferential stress. As I just mentioned, right, stress is calculated as force, I can say sigma is calculated as force by area. So, if you want to calculate force, it is the product of stress into area. The stress we are talking about is the circumferential stress. So, P can be calculated as the product of circumferential stress into area, correct. So, So, I can say 2 times, correct, circumferential stress into area, correct, should give you P, right, 2 times P, okay, minus F, the bursting force, right. We have understood how we normally calculate the bursting force. The bursting force is nothing but the product of the internal pressure, right, the internal pressure P acting inside the cylinder multiplied by the projected area of the curved surface on a horizontal plane, correct. So, it is nothing but the product of the internal pressure P into the projection of this, which is nothing but the diameter d, internal diameter, into length, correct, into d into L, right. So, that is pressure into area will give the bursting force. When you say this area, it is the area of the curved surface on a horizontal plane, correct, that is diameter into L. This has to be 0. Now, the next important thing is the area here. What area? Okay, and what area this stress is acting? So, obviously, it is the thickness multiplied by some length. It will be having some length L. So, you need to understand. So, that is 2 times sigma c into this area is calculated as T into L, thickness multiplied by length minus P into dl equal to 0, correct. So, here the length, right, will go off. So, we can just try to push this 2t on the other side, or 2 times sigma t equal to P into d, or we have the most important expression that we are talking about, which is nothing but sigma c equal to P into d by 2 times t, right. So, what you need to understand here is the circumferential stress can be calculated as, okay, the ratio of P internal pressure into diameter, internal diameter, divided by 2 times thickness, right. So, it is a very simple expression, okay, that we can talk about. So, if I just try to just take you through, okay, the equations. So, the same one that we are trying to talk about, minus F1, I am calling this as F1, F suffix 1 plus 2P equal to 0, okay, downward minus upward positive, and as you understand, the bursting force is calculated as the product of P into the thickness into area, okay, and length, and the next one is the pressure is calculated as stress sigma c, okay, into T into L is what we are trying to talk about over there, okay, and I have substituted these values, and then we have got the stress sigma c as P d by 2T. So, some important information that you need to understand with respect to this most important expression, that is the circumferential stress, okay, increases with P, that is more internal pressures, okay, the sigma is going to increase. Like I have a cylinder, right, and then I have some internal pressure 1 megapascal, okay, is calculated as PD by 2T. So, same cylinder, if I subjected 2 megapascals, the circumferential stress increases. So, here as P increases internal pressure, that is the circumferential stress directly increases. The next one is the diameter, right, as the diameter increases, okay, 1 meter internal diameter pipe, then I have 1.5 internal diameter pipe. So, we can understand that that is for the same pressure and thickness, right, the pipe with 1 meter diameter has lesser sigma c when compared to a pipe which has 1.5 meter internal diameter P. And coming to the last one, the thickness, right. So, thickness, it is in the denominator. So, if the thickness is more, stress is less. If thickness is small, stress is more, right. So, these are 3 parameters which influence the first stress in a thin cylinder, that is something but the circumferential stress. That is, as the pressure increases, the circumferential stress increases, as the diameter increases, the circumferential stress increases, and as the thickness increases, okay, the circumferential stress reduces. Well, students, okay, we have just come to an important stage here. So, we will just close the presentation. So, right now, and we will be back in the next presentation, okay, where we try to take expressions, okay, for the next important stress, that is nothing but the longitudinal stress. Thank you.